Okay, covering page 7 and 8 here. We'll look at these reciprocal function graphs first. We want to locate the shifting. So this +3 that's with the x, that indicates that it's a left shift. Always opposite when it's located with the x. So what I want you to recall here is when you have a reciprocal function, typically there's an asymptote running down the center and another one running across the center. Okay, so that's where they begin, but the ones that run, well, the shifting then can move that. So if I need to go left 3, there's no way to move this one left. It's just going to stay on that line. This is the one that can move left. So I move it 3 to the left, and now I have my new asymptote. Okay, so we always have two asymptote lines with a reciprocal function. It's just a matter of whether either of them got shifted. The next thing to look for is a stretch factor. There is none, and so the way it gets graphed is exactly 1 unit above and 1 unit to the right of the first intersection point. And then you do the same thing in the other location, and then you can make your graph. And your graph is supposed to be a curve that approaches those asymptote lines, and then another curve that approaches the asymptote lines. Okay, so that's a pretty basic version of this. I just want to comment real quickly here that if this was a -1, if this was a -1 over x plus 3, you would still have a left 3 shift. So we would still use these same asymptote lines, but the negative would reflect the graph this way over the x-axis. So anything that's here is going to move up to the upper left, and it would make a curve like this. And anything that's here would move down to the lower right, and it would make this curve. So the reflected version with a negative just goes into the opposite quadrants. So the blue equation is represented by these blue curves. All right, so back to number 48. We'll start with our 0 asymptotes. And where are they going to get shifted? Well, the -2 here indicates that it's moving to the right. And the -4 after the fraction is going to be a downshift. So if we take this vertical asymptote and move it to the right 2, and we take this horizontal asymptote and move it down 4, the graph is now recalibrated to satisfy those shiftings. Okay, and it's 1 again. So we just go 1 unit. 1 unit away. 1 unit away. Make our graph. And that's that. And while I'm on this one, I do want to just remind you that you could have a stretch factor. So I'm just going to say, what if we had a 4 here in the numerator instead of a 1? All the same shifting would have occurred. The 4 in the numerator doesn't affect the shifting. What it does is it tells you how stretched out the graph is away from the center. So from this intersection point, I'm going to count 4 units, 1, 2, 3, 4, and put a blue dot there. And then going up, 1, 2, 3, 4, put a blue dot there. If I connect those with a curve, you can see that the graph stretches out away from that center, right? Do the same thing here. 1, 2, 3, 4. 1, 2, 3, 4. Make that connection. And they still approach the curves, but it's just pulled away from that point. The thing to avoid, if you have a number there, you don't want to count 4 by 4 and start your dot here. That's not how it works. It's going to be 4 in each direction, and then you connect those up. Okay, so the equations in 49 and 50 are both with proportions. So we can just do a diagonal this way, and we can do a diagonal this way, and just multiply those and set them equal. So on the yellow diagonal, I have 7 times x. On the green diagonal, I have 4 times x minus 6. So if I distribute here, I have 7x equals 4x minus 24. Bring your x over, it's 3x. Divide your 3, you get -8. And if you check back, what you're looking for on these is, do we divide by 0 ever? So if you put a -8 in here, it's okay to get -14. As long as we're not dividing by 0, we're good. So this works. Okay, and the same thing with number 50. Let's do a cross product this way first, and then we'll also do a cross product this way. So for the yellow, I have x times x plus 5. For the green, I have 3 times x plus 8. So distributing gives me x squared plus 5x. Distributing here gives me 3x plus 24. All right, and then bring everything to one side because I have a square, so I'm going to need to factor. So if I subtract the 3x, I'll have 2x. Subtract the 24, I get minus 24. And now I can set up my binomials. So x times x. 24, I'm going to use 6 times 4 so I can get 2. And then plus 6 minus 4 should get me plus 2. Do a quick solving chart here. X plus 6 equals 0, so x equals negative 6. X minus 4 equals 0, so x equals 4. Did I divide by 0 anywhere? No. So neither one of those numbers is going to create a 0, so x is equal to negative 6 and positive 4. Okay. Now these don't work the same way because these do not have just a single fraction on each side. So what I need to do here is look at the three denominators and figure out what can I multiply this whole equation by that would incorporate all the factors of these denominators. Okay, so I have an x and 2 of them, so I definitely need to use x. I also have a 2, so I definitely need to use 2. And there's no other factors anywhere. So 2x is my LCM. All right, so when I go to do this, I would take this original, well, this is 2x over 1. So when I multiply it in, what I'm really doing is multiplying this 3 times 2x, and then the denominator would just stay x. And then when I do the second fraction, it's 1 times 2x, and the bottom stays 2. And on the third fraction, it's 12 times 2x, and the denominator is x. So the LCM I discovered is being used in each of the three numerators. Now let's do some reducing. On this first fraction, the x's will reduce, and 3 times 2 is 6. On the second fraction, the 2's reduce, and so I just get x. On the third fraction, the x's reduce again, and 12 times 2 is 24. So the goal here is that ultimately you get an equation with no fractions. That's the idea when you're doing this strategy. So if I subtract the 6 over, I have negative x equals 18. Divide the negative 1, and x equals negative 18. And then I just double check to make sure there's no dividing by 0. We're okay. So x equals negative 18. The hardest part about those is just identifying what to multiply it by and converting the fractions. But once you get that, it's very simple at the end. All right, so 52, my denominators are 3x, x, 2x squared. All right, so for the numbers, I have a 3 and I have a 2. So the LCM of those two numbers would be 6, right? Because that incorporates both factors of 3 and 2. For the x's, as long as I take enough x's to accommodate the highest exponent, I'll be good. So using an x squared here is going to be enough to accommodate these single x's, and it also will do the x squared. So whenever you have multiple exponents, just pick the highest one, and then you'll be good. So I'm going to do the same exact procedure that I did last time. Take the original numerator, this is over 1, the original numerator times 6x squared over 3x. Take the original numerator in the second fraction, which is 1 times 6x squared is 6x squared over x. And then I have 6x squared times, well, let's do it the same order. We have the original numerator, x plus 2, times 6x squared over 2x squared. So in each case, I put the LCM into the numerator next to whatever was already there. And then I just divided by what was already there. Okay, so this one would be 24x squared divided by 3x. This one is 6x squared divided by x. And this one is, well, let's just keep it the way it is. We'll do x plus 2 times 6x squared divided by 2x squared. Now I'd like to reduce. So 24 over 3 becomes 8. X squared over x becomes x, because I just subtract powers there. On the second fraction, there's a 6. X squared over x is x. And on the third fraction, I'm going to cross out the x squareds here, because those are multiplication factors. I'm also going to divide 6 by 2 and get 3. And so what I have in this conversion is the 3 times the x plus 2. And there's no denominator anymore on all three of these. That was the whole point, is to get an equation with no fractions. Okay, so 8x minus 6x is 2x. Distributing the right side, I get 3x plus 6. Take the 3x and move it over, and divide the negative 1. Okay, go back to the original problem. There's no dividing by 0 when I use negative 6, so that's okay. So these last two are the trickiest ones, there's no doubt. You have to locate the LCM by looking at the denominator and using all the factors. Then you need to use that LCM in all the numerators, and then do some algebraic simplification so that the fractions reduce to non-fractions. And at the end, it's simple. All right, over to page 8. All right, so looking at number 53, it looks like I have multiple categories. I have shirts, I have pants, and I have jackets. So when I have multiple categories, I need to multiply all three. It's called the fundamental counting principle. So I take the 7 shirts, I multiply it by the 3 pants, and I multiply it by the 2 jackets. All right, and that's going to come out to, let's see, we have 21 times 2 is 42 ways. 42 ways to arrange, well, let's see, just say 42 outfits, because that's what we were counting here. 42 outfits. All right, so anytime we have multiple categories, that's how we're going to handle that. When we have a single category and we're picking a smaller number from it, we have to decide, does it matter what order we take them in? Like, are we making an arrangement, or is it just a group? In this way, it's just a group of 5 markers, so the order doesn't matter. So between the options of combinations and permutations, combinations is the one that doesn't matter. So we take our total set, we do a combination with the smaller set, subset, so 16C5. You can enter that onto your calculator. Remember, you have a probability button, and you locate the capital C there, and you can do it that way, and that's going to give you a total of 4, 3, 6, 8. If you're on a graphing calculator, that's the math button, arrow to probability, and choose NCR. If you're on a scientific calculator, there's also a probability button, and you have to choose the one that says NCR. You just have to enter the number, and then the NCR, and then the new number. So it just depends on what calculator you're using. You also could use the formula, which is n factorial over n minus r factorial times r factorial. So in this case, n would be 16. N minus r would be 11. And then r would be 5. So you could enter it that way too, because all of your calculators have that factorial feature also in the probability menu. So you could do it that way too. You would make a fraction bar first, and then put these components into each location. But it's definitely faster if you have a calculator that will do NCR. Okay, number 55. How many ways are there to elect a president, vice president, secretary, and treasurer? So this is an arrangement. We're defining specific roles here. So in this case, the order that I select them will matter. But it's still just a single group I'm choosing from. So the 32 members, that would be my N. The 4 roles, that would be my R. So I'm going to do a permutation this time. So we'll do 32P4. So I'm choosing 4 members from a set of 32. And that works out on your calculator to be 863,040. That's if you have the NPR feature. If you don't, the formula is n factorial over n minus r factorial. So we take the 32 and we're dividing it by the ones we're not using, so 32 minus 4 is 28. So you set up a fraction bar and you put those factorials in. Get the same answer. So it's just a matter of what your calculator can handle on that. Okay, number 56. We're trying to find the probability, so we need to do a fraction for this. We have 30 total lottery balls. Select an even number, replace the ball, then select a multiple of 4. All right, in any set of numbers, the evens, there's going to be half of them, right? So from 1 to 30, there are 15 even numbers out of 30. Now, since I'm replacing the ball in the second fraction, which is done with multiplication, I also will have 30 balls available because I did not leave it out. I put it back in. Select a multiple of 4. So that could be a 4, could be an 8, 12, 16, 20, 24, 28. So those are all the balls in the bag that are multiples of 4. There's 7 of them. So 7 out of 30. So if you multiply that out, it reduces to 7/60. Okay, if you did a decimal version, that's okay too, but you'll be rounding, so the fraction is more exact. All right, number 57. So we're in the same sample space here. We're still in a bag of 30 lottery balls. The 7 only occurs on one of those 30 lottery balls. But then we're putting it back in the bag. So we're still drawing from 30. We're selecting a number greater than 10. So that starts at 11 and goes all the way up till I get to 30. So there's 20 numbers in that set. So the second draw is 20 out of 30 because I replaced the ball. So whenever you replace the item, the denominator stays the same because we're pulling from the same sample space. So this would multiply and reduce to 1/45. All right, 58. We have a similar situation that we're selecting a single number. So there's only 124 in the bag, so that's 1 out of 30. Do not replace. So that means that the new sample space only has 29 in it. We want a number less than 15. So that would be from the numbers 1 to 14. Those are the ones that are less than 15. And the one that I picked was not one of those 14 numbers. So I still have 14 balls in the bag that are less than 15. So that's my numerator. But let's say that I had selected the 10. And then I want to select a number less than 15. Well, then I wouldn't have 14 options because I would have already taken one of them out. So just beware of what you have available to you in the sample space. Okay, multiply those fractions and it reduces to 7/435. Okay, so this last part is on this page is dealing with conditional probability. So I want to find the probability that a junior did not attend the prom. So I'm specifying that we are dealing with the juniors here, right? So because of that, I am only focusing on the juniors to solve this problem, right? And then of those juniors, I want to know which ones did not attend the prom. So I have 84 total juniors here, which means that my probability of selecting someone who did not attend the prom, given that they are a junior, would be over 84, and the ones that said no is 56. I don't care about the seniors that said no because it says a junior that did not attend the prom. So that fraction reduces to 2/3. All right, so that's that one. And the second one is similar. They attended the prom given that they are a senior. Okay, so probability that they yes prom given that they are a senior. Now I'm focusing on the seniors. And in that column, I have 116. And so of those seniors, it looks like 97 of them said yes to the prom. And that's not going to reduce. That's just 97 out of 116. But before we go any further with this set, let's talk about another way that this problem could be worded. So let's say that this first problem said the probability that someone who did not attend the prom was a junior. Well, if I worded it that way, now I would be setting the condition that I'm only looking at those that did not attend the prom. So I would be only looking at this bottom row. This bottom row adds up to 75, and so my denominator would be 75. Or in problem 60, probability they attended the prom given they're a senior. Well, I could have worded that and said, what's the probability that someone who did not attend the prom, who did attend the prom, was a senior? Well, now I'm specifying the condition that they, yes, attended the prom. I'd be looking across this top row. So that would be 125. So you just have to be careful about what condition is being set and then only look at those options. The other way this could be is just an overall probability. So what is the probability that a student who's surveyed is a junior who said yes? Well, now I'm talking about the entire survey, all 200 students. And so it would be 28 over 200 in that scenario. So it just depends. Are you limiting yourself or not when you're doing these conditional probabilities? All right, so that's it for this page 8.